Welcome everyone. In this lesson we're going to keep with our critical points and we're going to see how to actually classify them. And our main test here is going to be the second derivative test. So first of all, let's remember, what does it mean to have a critical point at some point AB? Well, what that means is both the x partial derivative and the y partial derivative of our function at that point are both equal to 0. All right, so let's suppose that we've found our critical point. We've calculated both of the x and y partials, set them equal to 0, solve for x and y, and we got our point. And maybe we have more than one critical point. How do we know what's actually going on? So we're going to use this second derivative test, and let's read through this. So suppose that we have our second order partial derivatives of our function. They're continuous on a disk centered around AB. So they're the derivatives, these second order derivatives are nice. And let's suppose that AB is actually a critical point. So we've done the x and y partials, set them equal to 0, and solve for x and y, and this is one of the points that we got. We want to know how to classify it. And so we're going to calculate this gadget called D. And this is going to give us information about what's going on. And so it's the second order partial f double x times f double y minus the mixed second order fxy squared. And we're going to take our critical point and we're going to plug it into this gadget D. And a way to kind of remember how to calculate this gadget is with a little determinant here, a little matrix, 2x2 matrix. So kind of along the top, the columns here are x and y first order partials. Or second order partials, and then along the rows here, again, x and y partial derivatives. So the first spot here is f double x. The second spot here in the first row is fxy. And then we have fyx and then f double y. And if we do the determinant of this, just like if we were kind of doing like the cross product, we do a little determinant, multiply down the main diagonal first. So we get f double x times f double y, and then we subtract, and then we multiply down the other diagonal. And let's just remember, these second order partial derivatives are usually equal to each other by Clairaut's theorem. So we're just going to call that fxy since they're equal, and it's squared. All right, so let's just remembering how to calculate a little 2x2 determinant there. All right, so let's suppose that we've actually calculated this. If we plug in our critical point and we find that D is positive, well, then we actually have to look at the second order partial, f double x. And if that's positive, then we have a local minimum. If we find that D is positive, but f double x is negative, well, then our function actually has a local max. Okay. And if D is negative, well, what's going on? Well, then our function does not have a local max or a local min at this critical point. And actually something special happens here. We're going to call this a saddle point, and we're going to see what this looks like. And then if D is equal to 0, the test is inconclusive. So we might have to do something else there. And we're probably not going to see this too much. Most of it is going to be these kind of first three cases here. All right, so let's kind of look at the results of this theorem a little more closely, because we're going to be able to remember what's going on here using what we've known about kind of the Calc 1, the one variable version of our second derivative test. So it's very similar here. So with the results in mind, let's say we calculate D. So let's say we've calculated D and we've plugged in our critical point. Well, there's kind of three options for what D could be. So D could be positive. D could be negative. Or actually, let's put D equal to 0 there in the middle, and then or D could be negative. So there's three options. Once we calculate what D actually is at our critical point, it's either a positive number, it's 0, or it's negative. And if it's 0, the test is inconclusive. So we're not sure. It might still be a max or a min, or it might be a saddle point. We just don't know. The test is inconclusive. If D is negative, this is going to be our saddle point. And now if D is positive, we have to look at f double x. And we have to then consider this second order f double x. And there's kind of two cases we're going to consider. Either f double x is positive, or f double x is negative. Now, if f double x is positive, we want to think of the second order derivative as kind of telling us about the shape of our curve or shape of our graph in the x direction. So we want to think of f double x as really giving us the concavity in the x direction. And we want to think of f double y, again, as giving us the concavity of our graph in the y direction. And so we want to think of these second order partials as giving us some information about how the graph is shaped, the concavity. So if we're looking at f double x, what does it mean if our second derivative is positive? Well, if the second derivative is positive, that means concave up. And it's helpful to remember the second derivative test if you actually draw in what the shape actually looks like. So concave up looks something like this. So our graph is going to have that kind of shape in the x direction. And if we draw in what that looks like, it's then clear that we're going to have a low point. So this is going to be a local min. Now, if the second derivative is negative, well, negative, if we're thinking back to Calc 1 here, negative second derivative means concave down. And so if we draw our concave down shape, it's kind of clear then what's going to happen. We're going to have a high point on our graph, so a local max. So the way we're going to be working with our second derivative test here is we're going to calculate this gadget D, which is we're going to be able to remember using this little determinant here. If D is 0, the test is inconclusive, then we have to kind of do some extra work. If D is negative, saddle point, we're done. If D is positive, then we have to look at the shape of our graph in the x direction, or really we could also look at in the y direction, so f double y. And if f double x is positive, that means our graph is has concave up shape in that x direction, which means local min. If f double x is negative, well then it means it has a concave down shape in that x direction, which makes it a local max. And so graphically, what these different possibilities look like, we might have a situation like this, where we have a local minimum at our critical point. And there's a few ways to think of this. You can think of this as at this low point, it's higher in all directions. Another way to think of it, though, is that f double x is positive. So we have positive, we're concave up in the x direction, and we're also positive in the y direction. So you could think of this as concave up in the x direction and in the y direction. And that's what this looks like. We have concave up in basically all the directions here. Now for a local max, what we're seeing in the next case, we have the local maximum at our critical point. And what you're seeing here is that f double x is negative. So it's concave down in the x direction. And same thing for f double y. So in all the directions, our graph is concave down. Now, what about when our d value is positive? So if we were calculating the d value, f double x times f double y, this would be positive. We would have a positive times a positive. And then same thing in this case. If f double x times f double y, we'd have a double negative. So again, positive. Now, what's going on with our saddle point? This is what we have, and it's kind of aptly named because it has this saddle shape. So our saddle point is right there. And what's going on is one of the directions is we have a concave up shape. So you can kind of see that along the ridge here of our saddle. So that's a concave up shape. But then we also have a direction where it's a concave down shape. So maybe kind of like along here. So what's going on, and maybe let's say, one of the x or y directions is going to be concave up, the other one's going to be concave down. So when we have a saddle point at our critical number, we have kind of a mixed concavity. So concave up in some directions, and then concave down in others. So for a saddle point, it's not all concave up, it's not all concave down. There's directions. One of the directions is going to be concave up, the other one's going to be concave down. So you kind of get this saddle shape. Another way to think of it, though, for a saddle point is some of the directions you're walking uphill and some of the directions you're walking downhill. So it's almost like neither. It's not a max or a min. In some ways, it's kind of a max because in this, it's a low point, but then in other directions, it's a high point. So you're kind of stuck in the middle there almost. All right, so let's try an example. So let's find and classify the critical points for the function y squared minus x squared. So first of all, let's find the critical points. And that we're going to do with our first order derivative. So we got to calculate f partial x. So f partial x here is going to be negative 2x. F partial y is going to be 2y. We set each of these equal to 0. So this one's not too bad. And we get x equal to 0 and y equal to 0 when we do those. So that means if we put it together, the origin is a critical point. It's the only one. All right, so starting off kind of easy. And let's actually classify. So we're going to do our second derivative test. So let's set up this gadget D. So it's f double x, fxy, fyx, and then f double y. So now let's calculate our second order partial derivatives. So f double x is going to be negative 2. fxy is going to be 0. And then same thing, these are always these are always going to be the same. And then we need, for the last part here, f double y. So that partial derivative is going to be 2. So when we do this, we end up with negative 4. And since d at this critical point is negative 4, the d value here is negative, which means we have a saddle point at the origin. Okay, so a little practice there, and we're going to, well, try some more examples where we have to find and classify our critical numbers. So we'll look at those in class. We'll see you then. Bye-bye.